We all know that regular, routine maintenance is essential in order to keep protection and control schemes performing as intended. However, our best efforts at testing can only be as good as the accuracy of the measuring instruments and how we use them. The objective of this videotape is to look at fundamental testing techniques and see how we can avoid some of the pitfalls that commonly occur. When we talk about electrical measurements, exactly what kind of measurement do we mean? Well, depending upon the particular circuit, we need to know the value of at least some of the following properties: voltage, AC or DC; current, AC or DC; resistance; frequency; dB signal strength; phase angle; timing. So let's first take a look at measurement of voltage. These measurements may be taken by analog-type electromagnetic meters or, in recent years, digital instruments. One of our biggest concerns has to be the accuracy of the instrument. For example, this typical analog volt-ohm meter is liable to an error as high as 3 or even 4%. However, with this analog meter, the error is less than 1%. With digital meters, the accuracy is usually within 1%, except on the very inexpensive models. Digital instruments provide better resolution. The term resolution refers to the smallest reading increment that the user can observe. When using a DMM, be aware that the accuracy of measurement may not be the same for different types of measurements. For example, with this meter, the specification indicates a DC voltage accuracy of 0.1% of the reading, plus or minus 1 digit. However, if we select this instrument to measure AC voltage, then the specified accuracy falls. The tolerance for error is now 0.6% of the reading, plus or minus 3 digits. This is for a frequency within the normal range of 45 Hertz to 2 kilohertz. Note that an error of, say, 3 digits on the scale has less significance on a full-scale reading than one at the lower end. Bear in mind when interpreting test results that the margin of error may be plus or minus. For example, this particular voltage source is known to be set at 120 volts with an accuracy of 1%. This means that the voltage may actually be anywhere within the range of 118.8 to 121.2 volts. Now suppose we're measuring this voltage with an AC digital voltmeter, which is specified as 0.75% accurate. The reading indicates 120.9 volts. One interpretation of this is that the voltage is actually 120 volts, and the voltmeter is reading 0.9 volts high, that is 0.75% of 120 volts. However, it could be that the voltmeter is actually reading 0.75% low, in which case the actual measured source voltage would be 121.8 volts, outside of its specified limits. This example shows a worst case, which is not likely to occur in practice, but it does serve to illustrate the meaning and importance of instrument accuracy. In AC circuits, the accuracy may also be affected by the characteristics of the waveform being measured. To illustrate this fact, this test circuit is used to produce a distorted secondary voltage. Two different types of voltmeter are used. One responds to the RMS value of the voltage wave, and the other to the average value. As the primary current through the CT increases, the two meters indicate the same value within their respective tolerance. However, as saturation of the CT is reached, the indications differ. The readings on the two meters now differ by over 25%. This is because the waveform is very distorted at this point, and both instruments are calibrated for a pure sine wave. In practice, most power companies standardize on either the RMS or average type of meter only, so as to make sure all readings are compatible. Measurement errors are very likely to occur when using digital instruments in close proximity to electrical and magnetic fields. Here, we are trying to measure a small voltage across a high-resistance circuit which is located in a substation. The probability is that the nearby magnetic fields will induce a current into the meter test leads, and this in turn will produce a voltage which is superimposed upon the measured signal. Clearly, one way to reduce this error is to keep the test leads as short as possible. If you do have to use long leads, then twist them together throughout the length. In this manner, the interfering flux should be counteracted. When making voltage measurements, remember that the measured value can be affected by the impedance of the source itself. As soon as you connect the voltmeter to the circuit, additional current will flow, and this in turn will cause an additional voltage drop across the source impedance. Clearly, the higher the impedance of the voltmeter, the lower will be the additional current flow, and the more accurate will be the result. Typically, the DMM has an input impedance of 10 megohms, thus the loading effect is generally negligible. However, be aware of this problem when using an analog meter of lower impedance. It is good to remember that no circuit remains undisturbed when taking readings. When measuring currents in this live circuit, analog ammeters with less than 1% error are being used. Multimeter use is not recommended in this situation. Ensure that the accuracy level is suitable for the job. For example, when this digital multimeter is selected to measure AC current, we note that the margin of error is specified as 0.9%. This would not be adequate if we are, say, trying to adjust the output of a current transducer within a specified margin of 0.2%. The accuracy of adjustment can only be as good as that of the instrument which you are using for measurement. Consult the specifications when in doubt. Also, make sure that your multimeter is routinely calibrated. If you are measuring DC current in an inductive circuit, remember to reduce the voltage before interrupting the current flow at the end of the test. Otherwise, a large voltage may be induced into the circuit, causing damage to instruments and perhaps shock to personnel. In our activities, we are often concerned with measuring current flow in CT secondaries. The multimeter is not suitable for this job because it is fused. As you know, open-circuited CTs are a source of danger. If primary current flows, an extremely high voltage may be induced into the open-circuited secondary. For CTs and other current measurements, clamp-on current probes are most commonly used. One type of probe consists of a CT, usually wound with a convenient ratio of 1,000 to 1, so that 1 milliamp responds to 1 amp on the circuit being measured. The output can be measured by a multimeter or a millivolt meter with a suitable shunt. For example, 200 milliamps through a 1 ohm shunt would give us a reading of 200 millivolts. Another type of current probe is the Hall effect probe. This probe actually measures the effect of DC and AC magnetic fields around conductors. In this unit, an internal energy supply is required, so you must remember to check and change the batteries periodically. Although the input signal is current, the output of the Hall effect probe is actually a voltage signal, which can be measured by a DMM. You must remember to zero the output voltage before taking the reading. In this demonstration, observe the extreme variation in reading as the instrument gets closer to the magnetic field set up by the primary current. Note that this probe is subject to significant error when used in the proximity of magnetic fields from other conductors, for example in switchgear cabinets. It is evident that a magnetic field can significantly affect the reliability of the readings. All right, let's move on now to look at measurement of resistance. Most ohm meters work on the principle of injecting a small DC current, say 1 milliamp, into the circuit under test. By measuring the voltage drop across the circuit, the resistance can be calculated and displayed. It is important that the circuit be de-energized before attempting to measure resistance. Also, when measuring the value of a resistor in a circuit, you should always lift one lead so as to avoid the possibility of parallel current paths, which will, of course, result in a lower resistance value. You must take special care when measuring the DC resistance of an inductive circuit, for example, a transformer winding. If the test circuit is interrupted by removing the test lead, a high voltage surge will appear across the test terminals, probably exceeding the maximum allowable input voltage. One method of protecting against this problem is to connect a diode across the winding. The preferred method of measuring resistance in an inductive circuit is by measuring volts and amps, remembering to vary the current gradually. Most ohm meters have a resolution of about 1/10 of 1 ohm, which somewhat limits their application for measuring very small resistance values. For example, in measuring the contact resistance of switchgear, special equipment must be used. We will use a low resistance tester which provides a relatively high current at a very low voltage. While speaking of resistance, we must not forget the need to measure insulation resistance. This is, of course, a very high value of resistance that is normally measured by the megger. This instrument measures DC resistance, usually in megohms. It also produces high output voltage, thus suitable precautions must always be taken. Another very useful measurement which is used to check the deterioration of insulation material is the insulation power factor test. This special test equipment measures the AC dielectric loss through the insulation. The power factor actually refers to the energy loss in watts compared to the charging current, VA. For further information on this equipment, you will have to study the manufacturer's instruction manuals. Now, at this point, it's time for all of us to take a break, and then we'll come back and continue our discussion of electrical measurements. For now, though, please switch off the tape and review this material in your workbook. Now, continuing our discussion of electrical measurements, let's take a look at frequency.